Hi everyone, welcome back to the EBI Seminar Series. As we continue our theme, Biomass to Breakthrough, we're excited to be joined by Professor Douglas Clark, Chancellor's Professor of Chemical and Biomolecular Engineering. Today, he'll share how enzymes are unlocking the potential of lignocellulosic feedstocks like agricultural residues and plant matter, turning them into renewable fuels and valuable bioproducts. Together, we'll explore how these powerful enzymes work, what makes them so effective, and the innovative ways enzyme-driven bioconversion is transforming biomass research. Thank you for watching and enjoy. Hi, Doug. How are you doing today?
Good, Melanie. How are you doing?
I'm great. Thank you for asking. To start off, what exactly are lignocellulosic feedstocks and where do they come from?
So lignocellulosic feedstocks are basically non-food plant materials that are composed of three major components, one of which is cellulose. And that's a long linear chain of glucose, six-membered sugar molecules that are strung together and assemble into cable-like bundles. Then there is hemicellulose, and that's a branched polysaccharide that consists mainly of 5-carbon or pentose sugars, such as arabinose and xylose. There are some six-membered sugars thrown in there as well. And then there is lignin, which is a complex aromatic polymer, and that provides additional rigidity and pest resistance to lignocellulose. So lignocellulosics are actually remarkable materials. They're very well designed, if you will, and they're difficult to break down. But it's important to point out that unlike food-based feedstocks, they don't compete directly with the human food supply. So they avoid the fuel versus food debate that often arises with starch-based materials. So where do they come from? They come from many different sources. For example, agricultural residues, something called corn stover, which are the stalks, the leaves, the husks, and so forth, left over when the corn is harvested. Forestry residues, sawdust, tree bark, tree chips, so-called energy crops. And these are plants that are specifically grown or can be specifically grown to serve as a source of lignocellulose. So switchgrass, miscanthus are two of the common ones. And then there are municipal wastes, yard trimmings, a source of lignocellulose, waste paper. So the sources are abundant.
Now that we know what these feedstocks are, can you walk us through what happens from feedstock to fuel?
Sure. And there are many different steps involved. And this contributes to the complexity of the problem of generating biofuels from lignocellulose. So first, of course, you have to grow the biomass, and then the biomass has to be harvested and delivered to what is often called a biorefinery. Then once it's delivered, or maybe even before, it is shredded into small pieces, and then it's pre-treated in some way. And the pre-treatment is designed to make the cellulose more amenable to breakdown by enzymes, which we'll come to in a minute. And these pre-treatment methods can be mechanical, they can be thermal, that is, employ heat, or they can use chemicals or some combination thereof. So then once the biomass is pre-treated, then enzymes are used to break it down. So enzymes are proteins, and they're also catalysts. And a catalyst is something that accelerates a chemical reaction without actually being consumed in the reaction. So the catalyst can be reused over and over again. And the enzymes used are either cellulases primarily, they break down the cellulose, or hemicellulases, and they break down the hemicellulose, and then they release sugars that can be fermented by the microorganism. So then there is the fermentation process, and this is where microorganisms convert the sugar, that's the fuel for the microorganism, into ethanol or butanol or whatever the desired product is. And then that product has to be separated and purified so the fuels or chemicals can be distilled. It's the process of distillation for their final end use, and then ultimately distributed and transported to wherever it is that we used. So many different steps involved in this process.
I'm curious about the enzymes themselves, though. How are they chosen, and what qualities make an enzyme particularly effective for this kind of work?
So enzymes are really quite remarkable, and nature has done an amazing job in creating them. So the enzymes can be thought of as molecular scissors. So they literally chop up the cellulose strand. And some enzymes work from either end of the strand, or some enzymes work from the middle. So they work in harmony with each other. They're basically synergistic. And so they work together as a team. Hemicellulases do the same thing with hemicellulose. So they break it down into smaller sugars, which can be fermented. And then there are some other enzymes. They're called accessory enzymes that also work to enhance the accessibility of the cellulose through oxidative cleavage in one example. So the end result of all of this is a stream of sugars ready for microbial fermentation. Now, we could get much more detailed about this. There's lots of different types of cellulases, lots of different types of hemicellulases and so forth, but that's the gist of it. Cellulases and hemicellulases, and the cellulases work together as a team. What makes a good enzyme? So there are a number of things that we look for in an enzyme, and a number of qualities of that enzyme that we can improve through, say, protein engineering. And so the most effective enzymes are the ones that have the highest activity. So they break cellulose down the fastest, and you can use the least amount of enzyme with the most amount of cellulose. So the so-called highest specific activity of the enzyme. The enzyme should also be stable under the conditions where it's used, so we can reuse it over and over again without having to replace it. And ideally, if the enzyme is also active over a wide temperature range, that's also an advantage. And then we also want the enzyme to be tolerant to something called inhibition. And what I mean by that is either if the enzyme is slowed down by the presence of the product it makes, or if the substrate of the enzyme is present in a very high concentration and that slows the enzyme down, best if we can avoid that. So we can minimize product inhibition or even substrate inhibition. And then finally, we want these enzymes to play well together. So we want these enzymes to exhibit that synergistic effect that enhances the activity of the whole group. And then also very important, and so I know this is a lot, there's a lot of things we look for in enzymes. We want them to be relatively easy to make. And so obviously the cost of the enzymes is going to be important in the overall cost of the process. So we want to be able to make them in large quantities. So those are all the things that we look for. And I'm probably leaving some out, but those are the main ones that we look for in a good enzyme.
Beyond fuel, what other useful products can be made from plant-based feedstocks?
Well, there are many, many things that can be made from plant-based feedstocks via a microbial process, especially now in ways that we can engineer microorganisms to do amazing things. Question is, can they be made economically? But to address your question specifically, one class of products that can be made using plant-based feedstocks is bioplastics. And these include things called polylactic acid or polyhydroxy alkanoates. There's also what I'll call platform chemicals. And so these are a variety of chemicals that can either be used as the end product or can serve as precursors to other important products. Lactic acid, which can be converted to polylactic acid, succinic acid, adipic acid, 1,3-propane-diol, 1,4-butane-diol. So these are just a number of the different products that can be generated. And then there are other uses of the biomass. So the biomass can be burned to generate electricity. That's one end use. It can also be gasified through something called gasification, which produces something called syngas, and then that can be converted to hydrocarbons. And even the ethanol that is generated can be converted to something ethylene, which can then be converted to jet fuel. So lots of different options here. We have a lot of different ways that this can go.
Those possibilities sound promising, but of course, cost is always a key factor. What do you see as the biggest challenges in making enzyme-based bioenergy affordable?
Well, remember all those different steps involved? Well, there are challenges that are associated with each of those steps. And the fact that there are so many steps involved is a challenge in itself, and that also contributes to the cost. But to break it down, so one challenge is the high cost of producing the enzymes. So that's something that we'd like to have cost less. And so that is an active research area, is how do you bring down the cost of producing the enzyme? The lignocellulose is also resistant or recalcitrant to being broken down. And part of that problem arises from the presence of the lignin. So how to get rid of the lignin and what to do with it. And then, as I mentioned, there's the complexity of just having so many steps involved, and they're not necessarily compatible with each other. They don't use the same conditions, and so that contributes to the cost. And then the feedstock itself is difficult to work with. This may sound relatively simple by comparison, but when you harvest and break up biomass, you end up with this dirty, abrasive material that clogs pipes, fouls up equipment, clogs tanks that move it around and prepare it for enzymatic digestion. So just the nature of the feedstock can be problematic. And then remember, we produce multiple sugars. We produce glucose from cellulose, and we produce xylose from hemicellulose. And so there's multiple sugars involved, and the same microorganism doesn't necessarily utilize both sugars well. So there's the so-called mixed sugar problem. And then there's just the high capital cost of building a manufacturing facility. So that requires a significant investment. So the problem isn't hopeless, but it is complicated and has a lot of parts that have to be addressed.
Right. And how could advances in science or technology make the process faster or cheaper?
Well, there's a lot of ways, and we now have a lot of remarkable tools at our disposal to bring to bear on this problem. So first of all, enzymes can now be engineered to be more efficient, have higher activity, higher stability, and higher stability together, work together synergistically and so forth. So enzymes can be engineered in ways that really is unprecedented. People are also working at the process scale of combining multiple steps. So developing something called consolidated bioprocessing, where several of these steps are combined into one, and that will reduce the overall cost, at least in theory. Pre-treatment is also very important. So milder and more effective pre-treatment methods that convert the lignocellulose into a more amenable feedstock. Something called synthetic biology, which you've probably heard of, which can be used to develop new microorganisms that can ferment either multiple sugars together and or produce new desired products from those sugars. So these are ways that scientific research can be brought to bear on the problem. And then there's also something called process intensification, and that will no doubt utilize AI and machine learning more in the future to just improve the overall process and produce higher ethanol yields at lower enzyme loadings. So the good news is there are a lot of ways that scientific research can advance this problem.
Building on that, what role can government or industry play in helping this technology scale up?
Well, there's a lot of things the government could do, not necessarily without consequences, but for example, the government can set renewable fuel standards. That is, standards for the use of renewables that it has tried to do with limited success in the past. Uh, the government could also regulate carbon prices. And what do I mean by that? Well, the government can impose a so-called carbon tax. The government can propose or impose a fixed fee, say, per ton of CO2 emitted, something called a cap and trade system, which was considered very seriously several years ago, but wasn't ever really implemented. So the government can do things like that, but of course, the government can also invest in research. The government can fund basic scientific research. The government can partner with industry. Industry itself can help develop and invest large-scale demonstration plants to explore the feasibility of these processes and to optimize them. It can help build biomass supply chains. Where are we going to get the biomass? What is the supply chain? And in that regard, it can partner with agricultural and forestry sectors. So there are many different things the government can do, many different things that industry can do. And it's not to say that they aren't doing them, but sure, they could be doing more. And many things that have been considered and tried in the past have been abandoned and are no longer in effect.
And finally, looking at where we are today, are there any large-scale uses of this technology currently? If not, where do you see the earliest large-scale applications?
Right. Well, there are large-scale uses on the horizon, but they've been on the horizon for a long time. And one is the production of ethanol, of bioethanol, I should say, from lignocellulosic feedstocks. And there are currently no manufacturing facilities active in the US that are producing ethanol from lignocellulosics. But there have been some developed that have been put on hold or abandoned altogether. But people say it's still just a few years away. So there still is the potential for generating bioethanol from lignocellulose. And I think someday we will see it. Something that may happen sooner is the production of sustainable aviation fuels as airlines face carbon reduction mandates. And so that is another application for renewables. And there are renewable chemicals, such as those we mentioned just a few minutes ago, lactic acid, succinic acid, where profit margins are higher. So there's greater financial incentive. So there are a number of different opportunities that are just on the horizon out there that I hope will come to fruition sooner than later.
Well, thank you, Doug, for sharing your expertise with us today on bioconversion of feedstocks. We truly appreciate your work here, and we're excited to see how your research continues to grow.
My pleasure, Melanie. Thanks for your interest.
Thank you for tuning in to the Biomass to Breakthrough seminar series, where we explore how renewable feedstocks can be transformed into fuels, plastics, and other sustainable products. If you enjoyed the session, be sure to like and subscribe for more content on biomass conversion and the clean energy transition. You can also catch up on previous talks or follow us on social media, all linked in the description below. Thanks for watching, and we'll see you next time.